How to show it? So let Fn be Cauchy in L infinity. Okay. Consider the set A case. So if each of this Fn is in L infinity, so all of these are essentially bounded. Okay. In other words, they are bounded almost everywhere. Okay. So that means that there would be some sets. Okay. For each Fn, there would be a set on which is bounded, and there would be a set of measure 0 on which the Fn is not bounded at. So I'm saying that consider the set AK for which x, for which the Fk of x is bigger than the norm of Fk infinity. I can consider this. Obviously, this is going to have a measure 0, and by set Bmn, I mean the collection of the x for which a similar statement is true, but for the different set. Fn of x minus Fn of x is bigger than or equal to Fn minus Fm infinity. Why this would be the case? You can think about it. So if you take Fn and Fm from L infinity, and L infinity is a vector space itself, so this difference is also an element in L infinity. So the difference has to also satisfy this condition. It's pretty simple. Now combine all these sets, put them together. So union I equal to 1 to k equal to 1 to infinity ak, and the union, double union m going from 1 to infinity and put them together. By the way, let me tell you again, for each n you're going to have an an here, for each n. So as many as functions you have, as many as ak's you have here. Okay. And how many bmn we are going to have? From this infinite sequence, take any two and consider their difference. So the difference is obviously belongs to L infinity. Okay. So these make sense. It's important that we must realize that why the things are looking the way they are looking. By definition, since Fn are in L infinity, this must have a measure 0. And this also must have a measure 0. So the n must have a measure 0 actually. Okay. So set this, and the mu of n is the measure 0. The final thing is consider the x which is outside n. So we're going to say outside n, we are finite. Yeah. So consider x from n complement. Okay. Consider the x from n complement. Then, by the way, Fn's are what? I can treat Fn are the Fn at that point x actually. The general Fn, but Fn. So take a point x from n complement and consider the Fn of x actually. What can I say about Fn of x of this sequence? I'm sorry?
Bounded or not?
Okay, so it's bounded. But can you tell me even a more obvious thing actually than this? That would be a sequence of real numbers or complex numbers, depending on that. What is the domain of f? Okay, because f is a map from measurable space to R. R or C doesn't matter. But even if it is R or C both are complete actually. So that's a Kashi sequence in a real number set. So that will converge. So it will converge to some limit. Okay. So in other words, you're going to get a point by point convergence out. So hence this allows you to define a map actually. Okay. That for each such a point, you have a function which is the limit of fn of x, and that function is going to be the limit of this function. Okay. So let's finish up the proof. Final thing. खुदा साथ है खुदा समझ में नहीं कितनी पे होगा अरे ठीक है जी so for each x in n complement fn of x n is Kashi in CRR, but CRR both are complete. Okay, so they are complete. So what? So this fn of x is going to converge something. Let's define a function. So convergent. Let me write. Convergent. Let me define a function x. Okay. That is going to be the limit n goes to infinity. Fn of x. Okay. But on those x where the n is outside n complement. And how about when the x is inside, you give it a 0. When x is okay, so just assign it to 0. And then show it for yourself. Okay. That this fn and f in the infinity norm is this. What to do,